Alright everybody, we are going to create a trifold that's going to have all of the information we need for graphing quadratics. So the first thing I want you to do is get a piece of paper and I want you to fold it into thirds as if you were folding it exactly in thirds so that you have three places. You know, we have our factored form quadratic, we have our standard form quadratic, and then we have our vertex form. So this is just going to be a helpful resource for you while you're doing your assignment, the graphing quadratics assignment that's in your independent task folder. So now that I have it folded in thirds, I can label each one of these sections. The first section is going to be called factored form. That's the first one that we learned about, so we're just going to go ahead and put factored form. And then I want you to make this a little bit closer for you. And then standard form. And we're going to put all the things that you're going to need to remember about each one to make it easy for you when you're doing your assignment. And then of course the last one, which we just learned about fairly recently, is the vertex form. Okay, so quadratics all look the same. They're all parabolas. They're either upward facing or downward facing. They might be a little skinnier or more wide depending on the a value. So let's get started with the information I'd like you to remember about the factored form. And I'm going to say the example here is going to be x minus 1 and x plus 7. Okay, so that's our factored form equation. And some things that we want to remember about the factored form. First of all, we know that there are roots. Okay. Another word for roots might be x-intercepts or zeros or solutions, right? But how do we find the roots? Well, in order to find the roots, we are going to set each binomial in our equation equal to 0. So that's the very first thing that I'd like you to do is set each binomial equal to 0 to find the roots. Now, the roots are going to be ordered pairs, of course, because those roots are going to cross the x-axis. So I'm going to show this step right here where x minus 1 is equal to 0 and x plus 7 is equal to 0. And so when I solve this, I'm going to get the fact that x is equal to 1, and I'm going to get the fact that x is equal to negative 7. But when I write that as an ordered pair, when I say what the roots are going to be when x let me rewrite that. That's going to be when x is 1 and y is 0. That's my root. And then my other root is when x is negative 7 and y is 0. Okay, so here's my two roots for this particular quadratic. Okay, so the next thing we have to think about is, can we find the axis of symmetry? So I'm just going to abbreviate that, AOS. I think we're all familiar with that abbreviation. So axis of symmetry, and how do we find the axis of symmetry? We take the average of the roots. Okay, so we're going to take the average of positive 1 and negative 7. And so taking the average means we add them together. So we're going to add 1 plus negative 7 and divide that by 2. So according to my calculation, I get negative 6 on the top and 2 on the bottom. So my axis of symmetry is when x is equal to negative 3. So over here I'm just going to write x is equal to negative 3 because that's where on the graph we're going to have that dashed line at negative 3 on the x-axis. Okay, so after we find the axis of symmetry, then we want to find the vertex. So the vertex, again, just as a point of understanding what the vertex is. It's either the minimum or the maximum point of the curve. So the vertex here is going to be, if we look back here to our function, this function is going to be a positive function. So we are actually finding the minimum when we're finding the vertex for this particular equation. So to find the vertex, I'm going to plug the axis of symmetry into the equation. Okay, so -3 goes back into the equation, so I'm going to show that here. So my -3, which is my axis of symmetry, subtract 1, -3 plus 7. Now there is a multiplication sign right between those two, so once I figure out what the parentheses are, then I'm going to multiply the two parentheses together. Here I get -4, here I get +4. So my vertex is when y is at -16 and when my x value is at -3. Remember, the vertex is on the axis of symmetry. It always falls on the axis of symmetry. So let's write the vertex as an ordered pair. -3, -16 will be the vertex. Okay, and then we have the y-intercept. That's another part of our graph. Let me get one more color here. Okay, so my y-intercept, it's where the graph hits the y-axis, and that's when x is going to be 0. So the y-intercept, we're going to substitute 0 into the function for x. So it's when x is equal to 0, what is the y value? So I'm going to plug 0 in. So we're going to have 0 minus 1 times 0 plus 7. So my y-intercept in this case, -1 times +7, is just -7. Okay, and what we mean by that is if we write it as an ordered pair, the y-intercept would be 0, -7. Okay, so how does the factored form connect to the standard form? Well, we still are going to have many of these things showing on our graph when we have a standard form. We're just going to go about it a little bit differently. Okay, so it's possible that you would want to stop the video and kind of catch up with whatever I wrote here in case you got behind. And then, of course, restart the video to get started on the standard form. So in order to get this factored form equation into standard form, I can use the box method. The box method is just showing us to multiply these two binomials together. And when I do that, I should arrive at a standard form that looks like this. So it would be x squared plus 6x minus 7. Because remember, when we add these two values together, we get our b value. And when we multiply them together, we get our c value. Okay, so this graph is going to look the exact same. It's just that we're going to go about graphing it just a little bit differently. So we're not going to worry about the roots necessarily on something that has standard form, but the first thing we are going to find is our axis of symmetry. So the axis of symmetry, and to find the axis of symmetry, I already defined, oh, I didn't define it, did I? The axis of symmetry divides the parabola into two equal, or we could say reflected halves. Okay, now to find the axis of symmetry in the standard form, we're going to use this little formula, -b over 2a. Now, if you don't think of it as -b, you could think of it as opposite b. So before we start that process, let's go back up here and identify that a is +1, b is +6, and c is -7. Okay, so this is an important part of working with the standard form, is identifying the a, the b, and the c. Now, once we have our a, b, and c defined, we can plug the b and the a into our formula here to find our axis of symmetry. So b is positive, fortunately for us, because then we can just say negative 6 over 2 times 1. And we already know what the axis of symmetry is, because when we did it in factored form, we should still get the same value because it's the actual same equation, just in a different form. So negative 6 divided by 2 is negative 3. So our axis of symmetry is negative 3. And then, of course, just like we did before, we're going to plug the axis of symmetry into our function in order to find the vertex. So vertex, and we already know that that's the minimum or the maximum. We're going to plug the axis of symmetry into the equation, and sometimes I recommend that you use a calculator for this part. So negative 3 is going to go in there, so y equals negative 3 squared plus 6 times negative 3 minus 7. Now we already know what our vertex is, right? We did that over here, but let's just work this out to be clear. Negative 3 squared is 9, and 6 times negative 3 is negative 18, and then we have our negative 7. Let's just make sure here. Did I do something wrong? 9 and... no, that's correct. Okay. So we have y equals 9 minus 18, negative 9 minus 7, so y is going to equal negative 16. And again, our vertex is going to be the ordered pair negative 3 from our axis of symmetry, negative 16. Okay? So just remember that if you have something in standard form, you start with the axis of symmetry and move to the vertex. The roots are not the focus when we have a standard form graph. Okay, we still will have a y-intercept, and then there will be one more thing after the y-intercept, which is our table of values. So our y-intercept is still going to be where the graph crosses the y axis, so that means that we just need to, we could substitute 0 into the function for the first term and the second term, but that's always going to result in a 0, so that's why we say that our y-intercept is always the c value. So in this case, our c value is negative 7, so we can say that the y-intercept will be at 0, negative 7, because our c value is negative 7. Okay, the last thing that I want to point out here is that we want to create a table of values, because right now all we know is we know 1 point here and 1 point here, and remember we need 3 to 5 points to make our parabola, a nice smooth curve. So the y-intercept would work. The vertex is going to work. We could probably reflect the y-intercept over the axis of symmetry to get a third point. But what I'd like you to do is create a table of values with 5 points. To do that, you're going to substitute x values close to the axis of symmetry. And then don't forget that you can use the reflected points. Reflect each point until you have 5 ordered pairs on your table. Okay, so an idea here, just a clue on how you can get those values, just go to Desmos calculator and plug a number into here, or you can actually just graph this and you should be able to find plenty of points for your graph. Okay, the final way that we know to graph, or the final form that we have for graphing a quadratic, is in the vertex form. And some of you probably think this is a pretty easy form because it gives you the vertex and you don't have to do any of these steps to get the vertex. So that's great. Now if you need to stop the video and come back to it. If I've gone too quickly before you start the vertex form, go ahead and do that. So just a reminder that our vertex form is, it takes the form that looks like this, and of course there could be an a value out here in the front. For this particular equation, to make it match this one, remember that we would take the vertex, so the vertex itself would be written into the equation. So we would have y equals x, I'm going to say plus 3 here, because remember it's always the opposite value for the h, and then we would have minus 16, because we already know that the vertex for this particular graph is going to be -3, -16. So you may want to write a note to yourself that h is always the opposite sign. Okay, so we already know that the vertex is going to be -3, -16. So the first thing we want to do here is identify the vertex. And that's why it's called the vertex form. Because HK, this H and this K is always the sign that it says, but H is always the opposite sign. And then you can go ahead and sketch the axis of symmetry on your graph. So that'll be the second thing. Sketch axis of symmetry, which is just the H value, or you could call it the X value in the ordered pair there on your graph. Axis of symmetry is the H value. Okay, and once you have that sketched, and you also have the vertex plotted, I guess we could write a note, identify the vertex and plot it. Okay, now after you have the vertex plotted and the axis of symmetry, the next thing you're going to do is create a table of values. And so to create a table of values, you're going to do the exact same thing we said here, is substitute x values into the equation that are close to the axis of symmetry. And as I suggested, you could just do that with the Desmos calculator. So step 3 is to create a table of values. I'll put in parentheses using Desmos calculator, since that's the easiest way to do it. And we want a total of 5 points on our table to make a nice smooth curve. And so I would suggest you substitute, this is an asterisk here, substitute x values close to the axis of symmetry. So the table of values is just going to look like this, or of course it's just 5 ordered pairs that fall on your parabola. Okay, so I think that pretty much sums up all of the information we've learned about graphing in the 3 different forms for the quadratic functions.